Oh yeah, Biko, watch, You remember that displacement, please. Remember that displacement means change in position, is it not true?
Yes.
And we normally represent displacement with X or S. Do you agree? I can say that the symbol for displacement is S or X or Y. Hope you know. So if I know that for simple harmonic motion, displacement is given by A cos theta. Yes. Displacement is given by A cos theta. Very important to note that. Yes. And we know that this A here stands for what? Amplitude. Do you remember? Yes. Please, let's the noise. And from that equation where we got, when we did circular motion, and we have that W is equals to theta over T. From that equation where we got W equals to theta over T, when you make theta subject of the formula here, you see that this will come and times it. So theta is the same thing as WT. So that means that displacement is the same thing as saying X equals to A cos WT. Yes. So that is why you will see that everything simple harmonic motion is given by this. First of all, I started with saying that simple harmonic motion. Always know the difference between simple harmonic motion, simple pendulum, and spring balance. What I'm doing now is simple harmonic motion. All those ones like simple pendulum, spring balance, they are examples of simple harmonic motion. So I'm treating simple harmonic motion only. When I'm done with everything about it, I will now start treating examples of simple harmonic motion. So I said simple harmonic motion, first of all, when we started, before we said let's stop, I said that simple harmonic motion is defined as that type of movement, the to and fro movement of a body along a fixed path. I said it is the movement of a body in such a way that its acceleration and displacement moves in opposite direction to the restoring force. So that means that this is F here equals to minus MA, because F is equals to MA. But since we are talking about simple harmonic motion, it moves in opposite direction, so it's going to be negative MA. So which means that when I have F also equals to, I will have a situation whereby this is equals to X, or directly proportional to the displacement, sorry. But whenever we introduce proportionality constants here, it's going to be equals to, and if I introduce this equals to, it will have K, then the negative sign. I need duster, please. Someone should find me duster or hide it, please. Have you noticed that every day people come to this place? How much are they selling hanky now? 300. Every day people come here and they normally drop one for us to use as duster. And do you know one thing I've noticed? Let's say I finish cleaning the board now, here, and leave this thing and go. Tomorrow I will not see it. The thing looks like magic, and we are not paying attention to it. But there is somebody that is always busy harvesting hankies. That's what it means. I've noticed that every blessed day, if I forget hanky here, the following day, I will not see it. So somebody is busy doing something. So please, what that definition of simple harmonic motion simply says is these two things. So anytime you are thinking of simple harmonic motion, know it in a way that you are having F equals to minus MA, and you are having F equals to minus KX. So that means that if I put these two things together, I can have the sentence as saying minus MA is equals to minus KX. Is it not true? Minus minus can cancel each other. So that I now have that MA is equals to KX. Is it not true?
Yes.
So that if I choose to make, for example, a subject of the formula here, I'll say divide both sides by M. So that this will cancel this. So A is equals to KX over M. Now notice something. This K over M that I'm seeing here, this K over M I'm seeing here, we need to remember that in circular motion, we said that A is equals to W square X. Is it not true?
Yes.
Or W square R, yes. Is it not true? But we said that when we're talking about displacement in X-axis, A now becomes W square X. Yes. If you're talking about acceleration, sorry, in X-axis, if you're talking about acceleration in Y-axis, it becomes W square Y. Is it not true? Yes. So if I know that, it simply means that, remember that acceleration naturally for a simple harmonic motion is moving in opposite direction, which is minus MA. Is it not true? So if I carry this minus, this is the acceleration of simple harmonic motion is having negative. Remember the definition. Let's say I remove this m here. Is it not minus a you are saying? So if I want to equate for simple harmonic motion here, I'm not going to carry a. What I'm carrying is minus a equals to w square x. Let's say I'm using x now. So if I make a standard of the formula, this moves to this point. Are you saying it? Yes. So which means that anytime you want to get the acceleration of a simple harmonic motion with respect to angular frequency, what you're having is minus w square x. So if I still put these two things now together, if I put these two, this and this, if I put these two things together, notice that initially I'm having here, please notice that cos A equals to kx over m. So, and you know how I cancel that in. If I carry this now and equate to this will be the same thing as saying that I have minus w square x, Shebi, is equals to kx over m. So that notice something. If I choose to now check the x, I have x here, I have x here, is it not true? S can take care of x. So I'm now having minus w squared is equals to k over m. Is it not true? Yes. So which means that another way to look at this is that anything w, this minus is because of opposites in direction. So another way to think of it is that anytime I see k over m is the same thing as w squared. You need to note this thing. And which means that if I make w subject of the formula here, I will divide both sides by roots. Is it not true? Equals to roots k over m. This will cancel this. So another way to look at w is that w is equals to root k over m. So you need to know this. W, that is, I have a situation where I have, these two gives me the definition of what simple harmonic motion is. That is SHL. This one gives me the acceleration. What the acceleration is in relation to displacement. I get this, number 3. Now, comparing it to the equation of circular motion for acceleration. Sorry, comparing it to the acceleration of circular motion. And then, paying attention to acceleration, I have this fourth one. Then when I compare the two, I now have that the relationship W, that is angular frequency, angular velocity, has with this simple harmonic motion relation is that anywhere I see W, W is the same thing as saying roots K over M. And notice that at this junction where I have W squared equals to K over M, at this junction, this thing is, remember I still have this minus showing me that it's negative, it's moving in opposite direction. Don't forget it. So I can even transfer it to this point. I can make W sort of transfer it to this point to show that it moves in opposite direction. No confusion there. But at this point where I have that W squared is equals to K over M, I also need to note all these things I'm giving you are different ways that they can ask you questions, and it's important to have all these formulas. I can have that if this is over 1, this is the same thing as W square M or M square. Yes, let me use W square M or MW squared is equals to K. Look at it very well. Is it true? Shall we know that if this cross multiplies, W squared will come here. 1 times K is K. Is it not true? So I have another one, which is the 5th one. So it's important to note all these things because as we will be moving along the line, you will see us making use of all these things. So what we've done here is to talk about the displacement of a simple harmonic motion. We are not talking about pendulum. We are not talking about spring balance. We are just talking about simple harmonic motion. Because for example, if they tell you what is the period of a simple harmonic motion, in your mind you are thinking of 2 pi root L over G, you will fail it. The period of a simple harmonic motion is simply 2 pi over W. Finish. Very important. So you will still see us come to that. So I now know what displacement is. So I said that displacement is this. Now let's talk about the acceleration of a simple harmonic motion. Can I clean? Okay. Let's talk about the acceleration of a simple harmonic motion. Okay, let's talk about velocity first before acceleration. So let's talk about the velocity of a simple harmonic motion. Okay. K is a proportionality constant, or you say spring constant. So when we are dealing with spring, we call it spring constant. But it is just a constant. For simple harmonic motion, it's just a constant. But when we're talking about spring balance, we normally make use of it as spring constants. Can I claim? So the next thing, go and watch my video on circular motion so you understand how I'm calling theta WT. Theta is the same as WT. Please pay attention to what we are doing here. This thing should not injure me. Alright. I watch. The next one is velocity. We know that velocity is the derivative of displacement. Is it not true? That is, whenever you say change in something, all over change in time, that time you normally say all those things. It simply means that you should derive x with respect to time. That's what it means. Which means that if you come to this equation of x already is the same thing as saying that we should change a cos wt with respect to time. Are you seeing it? Yes, that's what it means. So we are deriving this, but notice something. If you come here, you see that what we have here is actually, we have cos, and cos is a function. Is it not true? Then we have another function here, which is wt. So that means that this equation actually has two functions. And anytime we have function of a function, what we make use of is what we call chain rule, composite function. That time when they tell you du over the x, then the u over the y. Yes, if you remember. Yes, in secondary school, Shebi, when they tell you at the end of the day, the x over the y now becomes the u over the x times the y over the u. Sorry, yes. So that you see that at the end of the day, this will cancel this, so that you still have that this is the same thing. Secondary school. But so what this thing means is that whenever you are doing this derivation, what you do is to derive cos first. And if you derive cos, what are you having? You have negative. Anytime you are taking the derivative of anything that starts with c, the end result will be minus. So you will now have that this is going to be, and when you are putting this, you don't make use of it. This is going to be negative. I have a sine wt. And please, there are some cases you see this thing to have something like face angle, like this. There are cases you see this thing like this. This thing now, this thing you're seeing here is called face angle. This one is called angular frequency. This thing means change in its angle in radians. So if, for example, I have that is at pi, when that movement is like this, at some other point, maybe this thing shifts now and is no longer, is now in this end. Maybe this part is like maybe pi over 2. So the change in the angle given in radius is what we call phase angle. All right, so if I know this, let me try to differentiate this. So I've differentiated the cos. I'm getting minus sine wt, Shebi? Okay, plus my phase angle. Is it not true? Check something now. Remember that what I differentiated here is cos, and I'm getting minus sine wt. I'm bringing back everything here. Now what you now do again is to derive, this time around you now do multiply by the derivative of wt with respect to time. Remember we said that this thing has two functions. Is it not true? It has cos function. And remember that this cos is the same thing as saying cos theta. Cos theta is going to be minus sine theta. Is it not true? So we've gotten that minus sine theta. And the first angle is a constant. I brought it back. Now again, I will still differentiate this one, this wt that is here. And when I differentiate this wt, you now see that what I'm having here is, let me bring out this thing. I have minus a sine wt plus the first angle. If I differentiate this with respect to time, this is going to be 1 minus 1. Is it not true? Which is 0. So I now have times w. So that if you bring it, you see that this is going to be the same as a minus, sorry, times this thing now. You see that, remember this one is a constant. So I will now be having that this is the same as saying a times that w. Then sine WT plus phase angle. Yes. Is it confusing?
Yes.
Is it confusing? All right. So please see why it's confusing you. The reason why it's confusing you is because you already know that cos theta is going to be minus sin theta. Is it not true? And remember that this theta, this particular theta, they are telling you when you get the function, still differentiate the angle. So I'm not just differentiating this. I'm differentiating this. And the time I've gotten this, I'll still come and go again and differentiate the angle itself. And theta here is actually WT. So when I differentiate this WT, I remember it's with respect to T. So if I differentiate this one, I'm having just W. So if you put it together, you now see that that's what you have. So that's the principle. The concept is not for us to just differentiate. In fact, as you progress to advanced differential equation, you see that whenever you have such a function like trig functions, you know that in mathematics, we do algebra before trigonometry now. Is it not true? So when I'm differentiating anything that carries that trig, I should get what trig is giving me. Then I will get what my algebra part is giving me. That's what I'm doing here. And the reason why I'm using multiplication to put them together is simply because of the fact that I'm seeing that angle, this angle that I'm having here, is already close, is already being separated with this by multiplication. So if it will be hard for you, how I want you to look at this is simply that you are doing this sin theta, then differentiating theta with respect to time. And remember that theta is something. Theta is WT now, is it not true? Yes. That's what you are doing. So that's just the simple concept there. You are doing sin theta. You cannot say just sine. There's nothing like sine. Are you there? Yes, you must have that your theta. There's nothing like cos. You must have cos theta. So that means you're differentiating sin theta and then differentiating theta with respect to time. That's how you do this. So even when I'm going to be getting the acceleration, that's still the concept you use for anything, not just here. Anything that involves trig and an algebra, you will differentiate the trig, then differentiate the algebra. So that's what I've done there. So that I now have AW sine WT plus phase angle. And this is angular frequency, this is time. So that means that my velocity, remember that this is velocity. That means that my velocity is equals to this. Velocity is equals to this. So this is my final answer. And please, what we are doing here is the equations of a simple harmonic motion. So we've been able to get the velocity of this simple harmonic motion. And please, mind you that the velocity we are getting here is just like that time you go to kinematics. You get that velocity is equals to U plus AT. You get that V square is equals to U square plus 2AS. You still remember those things. It's different from when I know that velocity naturally on its own is equals to S over T. Do you still remember? In simple harmonic motion, we'll come to that part. That time we'll now be checking when the velocity is at equilibrium, maximum. When it's at intermediate position. When it's zero, what are we checking there? But these ones are the equations you need to know. It's just like those kinematics that has the equations. So now we've gotten the velocity. So let's try to get the acceleration. Let's try to get the acceleration. And we know that acceleration, can I claim? Yes. So remember that what we are doing is strictly just simple harmonic motion. That's why I said the other time that what we did that day in class, what we're doing that day in class is just playing. Because I didn't want to video it because I was just teaching both simple harmonic motion, periodic and simple pendulum. But if you really want to learn this thing, you have to learn simple harmonic motion. Everything about it. Then you get to the parts where you are now learning the examples of simple harmonic motion. So, can I claim? So, using the same concepts now to learn to do acceleration, using the same concept, see what I will do here. Please, anytime you are differentiating, notice that the normal differentiation you know normally is maybe you are differentiating an algebra. But whenever you are differentiating an algebra that involves a trig function that involves an algebra, you apply this concept. Very important. So if I have this acceleration, we know that acceleration is the same thing as change in velocity. Is it not true? With respect to time. Now carry everything velocity and replace here. So that I now have that this is going to be the same thing as saying change in minus AW, should be sine angular frequency plus phase angle. And I already told you that angular frequency or angular velocity, sorry, that phase angle here is simply the shift or the locations of the angles. So in most cases you don't always see it, but it's proper you see it here so that you know everything. So I want to clean this part and stop at the end, at the last part. Okay, applying the same concept of differentiate sine theta, then differentiate theta. So let's apply the same concept. We know that if you differentiate sine, you get cos. Shebi, you know. But anytime you differentiate anything, even cos, anytime you differentiate anything that is carrying c, or any of those three functions that is carrying c, to give you a negative sign. So if I'm differentiating this sign now will just give me, watch please. Differentiating this sign, I will just have cos Wt plus phase angle. So I've differentiated it. Now applying the part of differentiate the angle now. So, and you know that the angle I'm differentiating here is Wt. Is it not true? With respect to t, do you still remember? So that I'm now going to have, if I'm differentiating this t with respect to t, 1 minus 1 is 0. So I'm having only w. Let me bring my w down. So now put it, you see that this is now going to be phase angle plus Wt. Then I have my cos. Now remember that everything here is a constant. I bring it down, minus a w. Now when you carry this now and multiply what you have here, you see that you have minus a w squared cos Wt plus phase angle. So, and that is your acceleration. That is your acceleration. Okay.
What if the institution now they don't give you that phase angle?
You don't, if they did not give you the phase angle, no need.
But so like for example, now that phase angle now is equal to kx, right?
Is equal to what?
Kx.
The phase angle itself.
Yes.
Do you still remember what we plotted? That force is what is equal to kx. Where we started now? No. See. Hey God. This thing now that you see, now, is a value that is in radians, or you say in degrees, but we normally take it in radians. This thing is talking about angle. This thing now. So what he's saying is that this your Wt that we know is theta in degrees, plus any change in the angle, which is this phase angle.
But sorry, but like this.
So a situation where I don't have this thing, it means that there's no change in the angle. So they are giving room, by the time you carry this thing and put it, what they are giving room for is that the angle can change. That is why notice that this W, I could have said let me come and multiply this thing here. But notice that I tried not to touch it, because I know that this thing is an angle. Is an angle on its own. So even this thing that you are seeing here, these two are together. Even without explaining, when I taught you measurements, I told you that once you see something being separated by a plus sign, and there are quantities, that you should take it that what this thing is what this thing is. If this one is in degree, this one is in degree. I taught you that in units and dimension. When I taught you measurements, where I said, for example, if I have ut plus half at squared, by the time you finish doing it, you see that this thing is giving you like L. This one is also giving you L. No need adding it up. So it's the same concept here. So that is why I did not touch it. So this is what I just have. And if you look at this very well, if you look at this thing very well, it is still looking like your displacement. So a shortcut I normally give my students is that if you know that displacement itself is A cos Wt plus phase angle, is it not true? That the acceleration is simply you coming to say, okay, you coming to say that this particular A here is having a W square outside that is having negative sign. Because notice that everything here is your displacement equation. Is it not true? The only thing that is strange there is this and minus. Is it not true? Yes. So if I know that I've gotten the displacement, the velocity, and the acceleration of a simple harmonic motion. So anytime I am given an equation or a question and they tell me, for example, let's say an example is given to me, they tell me that a simple harmonic motion has the equation y equals to 300 cos 150 t plus pi over 2. Remember I told you that this first angle is always given in radians, and the normal unit for angle is radians, just that we are fond of degree. Okay. So if I see this now, let's say they give me 300 cos 150 t plus pi over 2. Now after giving me this, now let's say they come and tell me find the angular frequency. Another name for angular frequency is velocity, angular velocity, which is W. They tell me find the angular velocity, or they tell me find the amplitude. So what would be my answer? Amplitude would be what? 300. That is this one, should be? Because what I will just do is to compare it with any of these equations. And even to make things easy for myself, since I'm not seeing minus, I just carry displacement and go there. Because I'll take it that y also means x, but when it's in the vertical axis. So I can just compare x equals to a cos wt plus phase angle. So that this one will be equals to this one. This one will be equals to this one. This one will be equals to this one. This is equals to this, and this is equals to this. So if they tell me find angular frequency, 150. If they tell me find amplitude, 300. If they tell me find the phase angle, pi over 2. They can even tell me find the maximum velocity. That is where we now enter trouble. And what you use for maximum velocity for simple harmonic motion is not what you use as maximum velocity for simple pendulum. It's not what you use for maximum velocity for a loaded spring. Because I notice sometimes, those of you that like watching YouTube or AI, sometimes they will solve something for you. They will just use the normal arithmetics. You will see that what they are using is the normal arithmetics of the basic concepts. They won't differentiate all these things. And whoever is marking it will easily see that, okay, I've catch you. So you need to know that if, for example, they tell you find the velocity of the simple harmonic motion, the formula you are going to use will be different from when they tell you find the maximum velocity for a simple pendulum. So because of that, we now know what simple harmonic motion is. We now know the equations of simple harmonic motion, and that the principle, the basic principle of deriving it is simply differentiate this the trig angle. Differentiate the trig angle, then also differentiate the angle itself. That's just it. So if I have sine theta, differentiate sine theta, then differentiate the angle. So which means that once I differentiate sine theta, I will always have W to it. So it's even easy. So that means that if, for example, they ask me find the maximum velocity of this simple harmonic motion, before we can be able to answer that maximum velocity, we need to derive the equation. So the next thing we are deriving is find it. They said this is number one, they say find the amplitude. Number two, find W. W is simply 150. They also said number three, find the maximum velocity. Find the max velocity of the simple harmonic motion of the SHM. So please, before we can do this, let's try to derive it. Let's try to derive it. And for me to derive the maximum velocity of a simple harmonic motion, I need to remember. I want to clean this, can I? Okay, please, we need to note that work is equals to force times displacement, should be? Is it not true? Yes. And remember that when we started, we said that force is equals to kx. Do you remember? That is for a simple harmonic motion. Do you remember? Yes. So I can put this force to be kx. Then s here, I'm using x again for it, so that I have kx squared. Somebody wants to ask me why am I using x? Remember I told you that for simple harmonic motion, it's either I'm using x for its displacement, I'm using y. A is when I have amplitude, that's maximum displacement. Anyway, I see R, I'm calling it L. So if I know that, I'm going to have that work done here for a simple harmonic motion is going to be kx squared. But because of the fact that I have what we call variation in this force and this displacement, I will introduce what I call half of it. And this formula you see now is what we call the potential energy of a simple harmonic motion. Half kx squared, that is how they get it. And we naturally know, I've taught you before, that kinetic energy is equals to half mv squared. I even derived this thing using those equations of kinematics. I still remember that I derived it. So we now know that we have potential energy to be half kx squared. And notice, force itself is also mg, is it not true? S can stand for h. Potential energy is not mgh. I've derived it. So it simply means that if I want to find maximum velocity here, I can first of all go and find energy of the system. I need to know what I call energy of the system of a simple simple harmonic motion. Sorry, energy of SHM. What I'm dealing with is just SHM. I've not started treating the examples. So energy of this SHM is simply going to be equals to kinetic energy plus potential energy. This thing is not for you to come and add it up. No. It's simply telling you that inside this thing is in joules. This one is in joules. What it's telling you is that whatever you have here should be equals to what you have here. Remember I told you that in physics, anytime you see plus or minus separating two things, it means that those two things are equal. Because for example, if I have AX plus BX, I cannot add these two things up now. But for them to tell me that two quantities can be added up or subtracted, it means that they are the same thing. So if I know this thing, what it simply means is that I can just say, okay, kinetic energy now is equal to half mv squared. Is it not true? Then this one now will be equal to plus half kx squared. So you already know it. So if I know that, I can now substitute the values of what I've discovered. What did we get as the equation or the formula for velocity? We said it's minus AW squared sine Shebi WT plus phase angle. Is it what you have? Yeah. Okay. If you like, you don't pay attention. Better be paying attention though. Why I say you should pay attention is that so that you don't go and mix up when we are treating simple harmonic motion. You don't go and mix it up with simple pendulum or spring balance. They are two different things. Even though they are the same type of motion. But the variation is, those slight difference makes the difference. So I will have that this energy of the system, let me represent it with E, will be equals to half, we will call that thing you have, M, sorry, let me give space. Let me clean this thing so that I will have enough space. So that I will have that E will be equals to half M, then the V is minus A, Shebi, WM square. Okay, WM. Okay, wait. Let me write this way. A, W, sine WT plus phase angle, Shebi? Yes. Is that all? Yes. Okay, notice that everything here is going to be in square, is it not to me? Because of this V is in square now. V square. So we are replacing V with this. So which means that this is the same thing as M A square W square sine square WT plus phase angle. Hope you know I don't have to square that one because the sine will take care of it. Yes. Now plus I have half K Shebi, then X, we have equation for it. A plus phase angle Shebi. Just be strong. Notice that once you start getting confused, you call me back. So that, okay, shall we, the x is having squared. Squared. So that this will now be the sentence as m plus half k, shall we? A we have square.
Yes.
Cos we have square. So that I have WT plus phase angle. Ahead.
I thought the other side the half be the
Wait, what?
kinetic side.
There's no 1 over 2.
There's, okay, yes, this half, Chevy.
Yes.
Thank you, sorry. Oh yeah, watch, go. Just be taking some. Thank you very much. Thank you very much. All right, please pay attention. Pay attention. Okay, I now have, remember, first of all, remember that this minus, we are raising this thing to square now, Chevy. There is square here. That means that that minus, by the time I raise it to square, will become plus. Do you still remember? So that is why when we are comparing these equations, or in fact, all those minuses that you normally see, let's put it this way, all those minuses you normally see, when you are solving, we normally overlook it. It's just telling us the negative direction. We always assume it to be negative direction, because one thing or the other always cancel it out. So, but if you want to insist on carrying it, you see that you end up complicating things for yourself. You will always get the answer. Maybe you get 300. You will not be saying, but it's supposed to be minus 300. Option might not show you that. Or even if the lecturer wants to punish you, just come and see minus 300, the first one, and you will fail it. So just have it in mind. But if you do it over and over, you will see that you will find a way to be always figuring it out. So now notice something. I have half MA squared. Please check so that we see that there is no mistake. W squared. Gotten from all these things. Then come here, we have half Ka squared. Because of this square. We have cos squared. Then we now have WT plus. Because if I have, for example, cos theta, we don't write cos theta square like this. How we write it is simply cos square theta. That's what I've done here. Because those WT and the rest are all angles. Everything here means angle. So if I know it, that is where we now go back to when we started this class. I told you that MW squared is the same thing as K. A catheteria?
Yes.
Do you still remember?
Yes.
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 You don't remember. Okay. Do you remember that when we compared W square X and K over MX, do you still remember? Yes. We cancel this. We said that this M can come over here, over 1, cross multiply. We have W square M, or MW square, is equals to K. Do you remember? Yes. Anywhere I see K here, I can replace it with MW square. Very important. Why am I doing that? Because you remember what mathematics is. Mathematics is always trying to say, if I see that two things, I'm looking for things that have unknowns. How do I get rid of everything? Or maybe how do I substitute so that they become the same thing? So I can see very well that I cannot be able to do, okay, I can even do it here. I can say, I have M here and I have W squared. Is it not true? Yeah. I can also replace it with K.
Yes.
Hope you know. Are you seeing it? So I can also replace this one with MW squared. So it's not up to you to choose the one you are using. Okay, I should use K.
Yes.
So I should use the MW squared to be equals to K.
Yes.
Okay, so that I now have that E is equals to half okay, Ka squared. Is it what you want?
Yes.
Okay, Ka squared. Shall we? Sine square WT plus phase angle. I'm happy that you are the one giving me the Ka squared. So that it's not like I'm the one putting it to you. You forcing you to agree to it. Half Ka squared cos square WT plus phase angle. Now, remember that this thing, everything I'm talking about here is energy equals to this. And this type of energy should be mechanical energy. Yes, when it has to do with movement. Okay, that means that I can easily say E is equals to half, I have Ka here, I have Ka squared here. Ka squared all into sine square WT plus phase angle. Sorry, remember, okay, I already have the half, yes. So plus cos square Yes, cos square, yes. WT plus face angle. Somebody will be somewhere murmuring, which one is this one now? Oh yeah, watch. If I carry everything here and times here, I have this thing.
Yes.
If I carry everything here and times here, I have this thing. Is it not true? So if I know that what that thing is trying to tell me is I want you to do for me, for example, do for me sine 30. I want you to check something. Then do for me cos 30. Add the two of them, what do you have? Just add the two. Do sine 30, do cos 30, what do you have? I have a reason for that.
1.366.
Approximately what? Approximately 1. If I write it up, it's 1, should it? Do for me sine 80 or sine anything plus cos 80. What do you have? Do for me, for example, sine 80. Then do cos 80. Add it up, let me see what you have. 1. Still 1, Shebi? Shebi, still 1. Anytime you have the sine of anything, sine theta plus cos theta, or sine square theta plus cos square theta, everything is simply equals to 1. That's what I'm trying to prove there. So in most textbooks you will see, and you know sine theta plus theta is equals to 1. That is how they get it. So if you do the sine of any angle, do the cos of any angle, by the time you add it together, it will always give you 1. It will not exceed it. So that means that what I have here now, everything I have here is simply the same thing as saying E is equals to times 1. So which means that E is equals to half Ka squared. Alright, that means that I can go back to that place I said that E is equals to half. Do you still remember that time I said Ke plus Pe? Do you still remember? Yes. That means that time I did half mv squared and half Ka squared. This one then becomes half Ka squared. Yes. So this thing now is the energy found on a simple harmonic motion. The energy found on a simple harmonic motion is simply given by half Ka squared is equals to half mv squared plus half Kx squared. And how do you derive this? Is by doing this thing that we've done here. We've derived E. So if they now want to add, if they now ask you what is the maximum velocity, if they now ask you what is the maximum velocity, that is where you now do the next line of action. Remember that we have a question that we are going to solve here. Remember we have a question to solve here, to answer to here. So let's try to derive.
Let's answer this one, then derive the other one.
You see which one? Which one? Answer which one? Tell me now. You see this one? We will answer it, but before we can answer it, we need to get velocity now. That's why. Yes. Want to get velocity. Thank you. You're welcome. Why is everywhere quiet? Okay, but see, can I clean small part of this one so that I can use the board? We'll be fast. I just want you to pay attention. Remember that everything we are doing is just simple harmonic motion. We've not started doing examples of simple harmonic motion. When we start doing the example with 3 simple pendulum, 3 loaded spring, 3 U2. Yes, oscillation of a U2. By the time we finish this thing, I want if you enter exam hall, you will see that you are not missing anything under each topic. That's if you are paying attention. Something that is finishing on Saturday. Something we are finishing on Saturday. By Saturday, we round up simple harmonic motion. You will see it now. By Saturday, we round it up. The remaining parts of the topic is very simple. It's those beginning part that was hard, that is hard. All the remaining parts are very simple, very few. And this simple harmonic motion, if you do it over and over, you see that it's just something that is together. Okay, I want to claim this part. Okay, see, if I want to get the velocity of this system, what I just need to do is to make velocity subject of the formula from this equation. So how do I do it? I will simply say this becomes half Ka squared. Shebi, this one crossing over becomes minus half, or I can just say half is common to all of them. Is it not true? I cancel all the half. So I now have Ka squared minus Kx squared is equals to mv squared. Shebi? On this side, I can see that K and K is common. I can just factor K out. So that I say A squared minus X squared is equals to mv squared. Making V subject of the formula, I can now divide both sides by I divide by M, divide by M. This will get out. So that I now have so you know that what each topic is teaching you is a way to think, like how to think. That's just what each topic is teaching you. So once I know this energy, anytime I want to find velocity, what and what do I put together? And it will even help you when we start treating work, energy, and power. So this is now going to be the sentence as saying K over M. Shall we see it? Then A squared minus X squared is equals to V squared. To make V subject of the formula, we can say divide both sides. Shall we? Yes. By this, the square root, we take the square root of both sides. So this now becomes the sentence as saying roots K over M, then roots A squared minus X squared is equals to V. Are you seeing it? And if we remember very well, there is a place somewhere that we did that W squared is equals to K over M. Do you remember? Yes. And we said take the square root of both sides. Then W is equals to roots K over M. Is it not true? Yes. I can replace this thing with W so that I now have W roots A squared minus X squared is equals to V. So anytime you want to find the maximum velocity, we can actually say that this is going to be V equals to W A squared minus X squared, or at equilibrium, because this thing that we found now is what we call velocity at intermediate position, or at any point. So velocity at any point, that is not the equilibrium, but at any point. Velocity at any point, or you say at intermediate position. Velocity at any point or velocity at intermediate position is this thing. This is the formula. But if I now want to find velocity at equilibrium position, velocity at equilibrium position, I will now know that velocity at equilibrium position means velocity at the maximum. Yes, somebody wants to ask me how. If, for example, I know what simple harmonic motion is. I say it's movement that goes to and fro, to and fro, to and fro. When it gets to this end, it stops, it comes back. Is it not true? Go again, come back. Notice that at the center part of this motion, the motion is too high. At the center part, there's no stopping. It's not feeling like stopping. But by the time it crosses that center, it starts retarding. It wants to stop. So that is why we say that at equilibrium position, velocity is maximum. So velocity being maximum means that there is no potential energy at equilibrium position. So when I'm going to be solving for maximum velocity, I don't make use of this potential energy. I just compare these two equations, these two formulas. So that I will simply have that to find the velocity at equilibrium, or at maximum, or to find maximum equilibrium, maximum velocity at equilibrium, to find velocity V at equilibrium, or you say maximum velocity. I will simply have that this is going to be half Ka squared. Ka squared is equals to half mv squared. At equilibrium position, at that maximum point, kinetic potential energy is not experienced. There is no potential energy. We know that it means energy at rest. It's not at rest. And please note that anytime they ask you what is the maximum velocity of a simple harmonic motion, you should be thinking of this formula. But when they tell you what is the maximum velocity of a simple pendulum, this is not what you are thinking of. You will come to that one. So you don't mix the two up. So if I compare this, making this under the formula now, I have half cancel half. So Ka square is equals to mv square. So I can divide both sides by what?
Okay.
By m, Shebi? Is it not true? Because it's v I want to get now.
Yes.
So this will cancel it. So that I have v square is equals to Ka square over m. So taking the square root of both sides, that is so that this one will be liberated. So I now have v is equals to square root k over m. Then and a square. And you know that this thing is essentially saying v is equals to square root k over m and then square root a square. Hope you know. If you times these two things, it will give you the same thing. So for that reason, I now have that v is going to be equals to, notice that a square and this is going to cancel out. So that I now have a. Then this root k over m means w. Is it not true? So I can just have this to be w. So velocity at maximum position or maximum velocity or velocity at equilibrium is simply AW or WA. Very important. It is steady, constant, it doesn't change. So anytime they ask you maximum velocity of a simple harmonic motion, it is simply WA or you say AW. Where A is the amplitude and W is the angular frequency or you call it angular velocity. Where A is the amplitude. Okay, even here you can say here, this thing is omega. And another name for omega frequency is angular frequency. This one is angular frequency or angular velocity. This one is amplitude. And do you remember what we called X? We said that X in simple harmonic motion means displacement. Do you still remember? This one is displacement. Or Y, yes. So remember I told you that at any position, whenever you are talking about intermediate position, which means velocity at any position, at those positions you can have displacement. But at maximum velocity or at equilibrium, notice that there is no displacement. Are you seeing this? Because at that center point where you have the lowest as it's moving this way, at that center point, this center point as it's moving this way, when it gets to this, it stops because the motion is too high. It moves, it continues. Okay, I think the best way to, should I say, understand what I'm saying is, if I have, for example, something this way, which is in that case of simple pendulum, you will notice that what they are telling you is that as this thing is moving to this point, it is not displacing because it is moving too high. That is, the minute it crosses this center point, that's where the movement continues. But at this equilibrium point, this center point where you have balance, it is to this end and to this end. If, for example, I have 2 here, I have 2 here. If this side is positive 2, this side is minus 2. Is it not true? Then plus 2 minus 2 should give me 0. Is it not true? Whatever effect this side is having, this side is cancelling it and is happening at the center point. So we say that there is no displacement there. And that is why at this equilibrium position, notice that there is no x here. Yes. So this is the formula for maximum velocity. And this is the formula for velocity at any point or at intermediate position. So if I know that, we can now solve this question. So find me the maximum velocity of this simple harmonic motion with what you now know. 300 times, which is what? So V will simply be AW, Shebi, which is 300 times 150. So V will equal to what? 45,000, which is in meter per second. So those of them that are not here, is video that they will watch. Because after they will tell me to repeat it. Even if you are tired as a student and you even have science students attached to your students, you are not supposed to be tired. Yes. So even if you are tired, you stay back. Yes. So since they are not here, they will use that and watch it. Okay. So that means we've gotten. Okay, I want to clean the board. Can I? Copy fast. Copy fast. If as a science student you've not gotten the study app, ask your classmates, your friends, what study app, let them send it to you. See if you notice that study app, it has all the PDF for both 100 level, 200 level, 300 level videos. And one thing you must know is that we are even still working on, that's why it's not on the Play Store, because when you upload an app to the Play Store, you can't edit it until after some months. If you don't have that features, until after that month then you upload another one, that's when you can get the update. So that study app will continue to be developed. So that even in your final year, you will not be saying medicine, everything about medicine, your course outline. You will see physiotherapy, because by then they might add it to radiography, you see it. So it will be very useful, such that even when you're in Parkley, even when you don't have time to always come and sit with us, you can always see the step-by-step course outlines to those courses. And why are we doing this? Because we know that for years, we've been doing this tutorial class, we've been having time with students, and it says that if they get to that level where they're always having choked up lectures, and they can't really have time to come for physical classes, they are seeing us physically, having time with us on the app, and they are being taught. So if you don't have that app, get it from your classmates. So when you get it, you can now come and activate it for you. And it's free. Once your tutorial student is free forever. There's no time in anywhere in the world. Nobody will tell you, come and pay special amounts for study app. It's not possible. If you're not tutorial student, you join tutorials. Yes. For that tutorial student, that's one of those things now. So when you get to your final year, what a situation whereby if you did not join tutorial, if you are getting to your final year, you will be missing us. You'll be saying, on year one, how I wish I paid for tutorials. Child. Because believe it or not, there are books that as you progress in level, that for you to get cost up to 20,000. Ask any medical student. There are books that if you are a medical student that you will buy, that cost up to 20 to 20 is small, that costs up to 100,000 textbooks. You will see people having it every year, it has this edition. You think I'm lying and quiet. So what are we going to be doing for you? You will see that in those apps, all those textbooks are going to be there. Some are there already. So as they are updating the editions, we are also updating the editions in our app. Yes. So that's the importance, the advantage. Okay. So let me clean. Let me clean this.
Yes.
And clean this. So I want to outline things to look out for under simple harmonic motion. So first of all, we've treated what is simple harmonic motion. Shebi? So somebody should define simple harmonic motion for us. Okay. We can also say it's a periodic type of motion. It is a periodic type of motion that involves the to and fro movement of an object or of a body about a fixed position. Wonderful. Is that why they brought the dead out? Okay, so we know what simple harmonic motion is, and instead of defining, having definition in mind, I can always remember it as a student by saying F is equals to minus MA in simple harmonic motion. Yes, because this thing is first of all directly proportional to acceleration, but negative acceleration. When we introduce proportionality constant according to Newton, we always introduce it with mass. That's the constant there, the body that will move. Because that's what this equation is. Every body, if you apply force or acceleration or movement, force to a body, that it will move in the direction of that force. So minus MA. So also F directly proportional to X. So, but Hooke's law, according to Hooke's, notice here we applied proportionality constant obeying Newton. In this one, we are applying proportionality constant obeying Hooke's. So this is now going to be minus. So F will be equals to minus K X. And anytime you put these two together, you will get something, if you remember. Yes. So that is all about that. Then we also remember that A is equals to W square R from circular motion. We derive this. So we said that since this is minus A for simple harmonic motion, if we cross over, because that A is equals to minus W square R. These are the things we derive. So the second thing is the equations of a simple harmonic motion. So we've derived the equations of simple harmonic motion. Number 2, equations of simple harmonic motion. Okay. Then the number 3 that we derive is the energy, shall we? Yes, energy of a simple harmonic motion. And anything that moves, just like you as a human being, you have so many energies. You need chemical energy, the food you eat, to have strength. Yes, when you are moving, you are, should I say, experiencing those mechanical energies as well. You stay small, your body, those foods that you ate in your body, and when you feel hot, it's not producing all those heat energy inside you. So as you are seated down or you feel sleepy, or as you are doing work inside you, you have lactic acid that makes you, as you stress more, that particular part of your body wants to get tired. Is it not true? So there are so many functions in you that experience energy. But when we are talking about simple harmonic motion, our focus is simply on the mechanical part of it. How is it moving? I will say that mechanical energy equals to kinetic energy plus potential energy, which we've derived. So the fourth thing we are doing here is velocity of simple harmonic motion, which we've gotten. So the velocity that we are looking at when we are talking about simple harmonic motion is simply is it at maximum or equilibrium? That, yes, or intermediate. That is it. So the fifth thing that we are looking at now under this simple harmonic motion is now what we call examples of simple harmonic motion. Examples of simple harmonic motion. Okay. Define that simple harmonic motion. Okay, I will define it in 3 ways. In fact, since this time around, I will not do it as a sentence. I will break it into tips. I'll break it down as tips. I'll break it down as tips. This one, people are looking for force up and down. Okay, my own is here. See, once it's an exam, you have to be very careful. Very careful, because this exam period, people are not smiling. Because if you check, there are people that all the foodstuffs they came to this school with has finished. Yes. And sometimes when you're in the university, that's when you learn that if you call your parents, they can be very wonderful sometimes. But when they get angry, they don't care. So there's a call you might make with your parents. The way they answer you will make you lose hope. So believe it or not, that hopelessness in some people will make them do anything to any student. And when you ask them, they say they are trying to survive. So please, once you have your phone, keep it well. Somebody today went to library to charge phone. Just plug, then I announce, I'm going to submit the assignment. Please look after my phone and come in. The same person that said look after phone, unplug the phone, and carry it. It's not a joke. You are there, Shebi. In real life, I'm not telling you something that did not happen. At the library today, and at the same time this thing was happening, in the chemistry lab today, FST, people were looking for their own phones as well. So it's phone massacre today. You will call the girl on phone. It's a girl that if you stole the phone, you call the girl on phone, she will pick the call. You say, hello, can you hear me? Say, yes. So she doesn't want to talk out long, so you don't hear her. So she wants to know if there's something you want to bring to the table. That kind of thing. But she doesn't want to talk. So when I told her, please, this phone return it, we will pay you for it or buy your phone. Yes. Very nice. So please. Yes, you need to be very careful. But see what we do. See what we do. Okay. Yes. Okay. Right. So see what we do, because I check the time, it's already 4. Come back, see what we do. We've done this, Shebi. So from tomorrow, being Friday, we will then know that what we are starting with is examples And remember that we've not solved any question here, because all the questions in your textbook we're supposed to solve it. Hope you remember. That's how we do our classes. Then, when it's marathon from next week, we're going to be solving all your past questions. So, from tomorrow we are starting with examples of SHM. And under these examples, we are going to be treating first simple pendulum. Simple pendulum. Then, we're going to be treating mass of loaded spring or oscillation of a loaded spring. And the important advantage of all these things is that when we are through with it, even during your exam, because you know you will still do practical exam. So as you do your practical exam, most of the things you're encountering there will be so funny to you, because you must have learned it very well. So now the fourth thing is now going to do the oscillation in a U-tube. Yes, if you like, go and be googling YouTube and say it's YouTube. No, we're talking about a tube that is in that shape. So once we are done with this, we'll now start our problem class.
What does the work energy?
Problem class. You say work energy and power. You say? Okay, work energy and power. Work energy and power is a topic on its own. Yes, this one is still simple harmonic motion now. And we've done the energy of simple harmonic motion. Work energy and power is a topic on this one, which we are going to be doing after gravitation. But next week is going to be for marathon. After our marathon class, give the exam. Are you aware that February, there is no exam February? It's March. And that March self, you are not even the one, you are not even the one starting first. So you understand it. Somebody said they say we are. Don't worry, you are the one teaching me the campus. So once it's that day, you will dress up and come. You will hire for 200 students. Don't worry. So please, we are taking this week that is coming for marathon. After the marathon week, then we'll go back to gravitation, then work energy and power. All right. So please, with that said,